We now invite Joseph Challenger from Imperial College London to give his presentation. Stand a little further away. Stand a little further away. Does it work?
No.
Maybe I could borrow.
Sure.
No, use that one. That's what I mean.
Ah,
I think he's cheap.
that's all right.
No, that's on me. Use the podium light. Put that one back. Use the podium light.
Is that better now? Okay, lovely. Thank you. I'm Joe Challenger. I'm a postdoc working with Tom Churcher at Imperial College. And I'm going to talk to you about some modelling work we've been doing on transmission blocking vaccines. So as we've heard from Camila, a transmission blocking vaccine prevents transmission from a human to a mosquito. So it's not giving direct protection to the vaccinee, but rather the idea is to develop a community level benefit. So typically the efficacy of a transmission blocking intervention is assessed by a mosquito feeding assay. This can be feeding mosquitoes on infected blood through a membrane, but it's also possible to do direct skin feeding. Once mosquitoes are fed, they're housed for a number of days and then dissected to see if oocysts have formed. So there are two different ways of measuring the activity based on the oocyst numbers. You can either look at the transmission reducing activity, which is just the reduction in the number of oocysts observed in the control and intervention arms, or you can look at the oocyst prevalence. So how many mosquitoes have you rendered infection-free as a result of your intervention? So these two measures are sort of intimately linked, but the numbers can be quite different. And what drives that is what some people call the parasite exposure. So it's the sort of mean number of oocysts found in infection events. So that leads us on to the question. So we can measure this in the lab, but how does this compare with what we find in naturally infected mosquitoes? So we've been looking at data collected in two sites in Burkina Faso where blood-fed mosquitoes were collected from the inside of people's houses, housed for 7 days and then dissected. And this was done at 4 different time points during 2014. And as you often find with this sort of oocyst data, it's highly over-dispersed. So the modal number of oocysts among successfully infected mosquitoes was 1, but the mean was 11, and there were a very small number of extremely high counts. And as well as the oocyst counts at these 4 time points, we have prevalence data in both sites collected at the end of the mosquito collection period. So our long-term aim is to incorporate a plausible TBV in a mathematical model of malaria transmission. This is a model that's been developed at Imperial over a number of years by Jamie Griffin and Asragani and others, and importantly incorporates naturally acquired immunity. So not all malaria carriers are symptomatic, and in malaria endemic settings, symptomatic infections are concentrated in the younger age groups. Equally, not all infections are equally infectious to mosquitoes. So we sort of assume that the higher density infections are more infectious than the asymptomatic ones. And amongst the asymptomatic ones, that the submicroscopic reservoir pair infection are less infectious than infections that are microscopy detectable. So we sort of set up the transmission model to roughly characterize the malaria epidemiology in the 2 study sites. This was based on the prevalence data that I mentioned, as well as what we know about net coverage and levels of pyrethroid resistance in the region. So pyrethroid resistance, just to get a sense of how well the nets are working, not just what the coverage is. And then in a sense, we sort of try and explain the URSIS data in terms of the mosquitoes that are sort of feeding on the malaria endemic population. It's probably simpler if... so here's the... so for one study site, we have the prevalence data collected at 4 time points during the year. So firstly in the dry season, and then in the peak of the transmission season, and then at the end of the transmission season. And if you calibrate the model to give this malaria prevalence, the model tells you sort of how many people it thinks will be symptomatic at a given time, how many people will be how many people will be asymptomatic but microscopy detectable in the purple. And then it also thinks that for this prevalence, you would have a submicroscopic reservoir of very low density infections that would not contribute to malaria prevalence measured by microscopy. So in the model, what we want to do is say, so mosquitoes are kind of sampling from this population, and that's what's explaining the URSIS data that we observe. So I'll show you the URSIS data now. So first of all, in the dry season, there were very few successfully infected mosquitoes, and the URSIS numbers were very low. So the data's in red here. Moving into the transmission season, you start to see sort of higher URSIS counts, although the mode is still 1. And in the peak of the transmission season, you get many more high URSIS counts. So I've truncated the distribution at 40 just because it's quite hard to show the whole tail. But it starts to give you an idea that you're starting to get more heavily infected mosquitoes. And our sort of hypothesis is that it's the It's the symptomatic infections shown in pink at the base of this slide that's driving these highly infected mosquitoes. Okay, so using those assumptions, we can sort of associate different parasite exposures with different types of infections in the model. And one reason we were really keen to do this was in high transmission settings, a big part of the infectious reservoir are from these asymptomatic infections of long duration. So to assess how a transmission blocking vaccine might work, you need to assess how feasible it is to block transmission events from these infections. Okay, so with those parasite exposures, if we know a vaccine's TRA in the lab, we can start to translate that into an estimated TBA in natural infection events. So moving forward, we aim to use data from ongoing clinical trials in Mali based on a vaccine targeting antigen PFS230 that's been assessed using both membrane feeding and direct skin feeding. This is work that's been led by Patrick Duffy and others in NIH and Issaka Sagara and others in Bamako. To get the ball rolling, we're using a simpler model fitted to data from vaccinated mice that was published a couple of years ago. So this is what the TRA model in that study looks like. So this is TRA as a function of antibody titer. This candidate was a PFS 25 candidate. So what the missing piece at the moment is sort of what are the duration of these antibody titers that are provoked by the vaccine. And until we have data on that, we're assuming, what would be the impact if those titer durations looked something like the RTSS vaccine, which have been very well characterized. So going back to these time series, with a high transmission seasonal settings. So again, in pink, the symptomatic infections, purple, asymptomatic, and then blue, asymptomatic but submicroscopic. What we can do is rescale these populations by how infectious the model thinks each type of infection is. So you can see if I go back and then forward, the blue area is really shrunk because the model doesn't think that the submicroscopic infections are very infectious. The pink area has grown a little bit, but it's these asymptomatic infections that are still dominating the reservoir. So if I introduce a vaccine at about 70% coverage in the population, you can start to see that a TBV could really put a dent in the asymptomatic reservoir of infection. The black line I've added is the mean daily EIR on the human population. So the level at which, the rate at which people are being bitten. So you can see we've taken quite a chunk out of it, but because it's a high transmission setting, it's still quite appreciable. We can also translate that into clinical cases. I realize I've put a lot on this figure. The three colors are assessing different age groups to vaccinate. So in blue, it's the entire population over 5 years old. Purple is school-aged children, 5 to 16. So they're contributing a big part of the infectious reservoir, or at least that's what the model thinks. And then these black lines trickling along at the bottom is just what you might find if you included the vaccine in an EPI program vaccinating infants. And I've just included that to underline that that's not what you would use this vaccine for, because although a lot of clinical disease will be in that cohort, they're not driving transmission. So it's important to realize when you model these interventions that you wouldn't introduce these vaccines on their own. They would be added to other interventions that are going on, in particular bed nets and indoor residual spraying. Bed nets in particular have been very effective at reducing malaria over the last 20 years. However, there's a limit to what interventions like bed nets can do due to things like outdoor biting and insecticide resistance. So one can view a vaccine like this as being a complementary intervention that you would use alongside bed nets. So I won't talk very much about sort of layering these interventions together, but this sort of the area in purple sort of gives you an idea of cases averted as we vary net coverage, and you could sort of hypothesize potential added benefit by adding a TBV, potentially in addition to a PEV such as RTSS, sort of on top of other interventions. Oh, and the word improve, it was a note to me rather than something that was supposed to say in the slide. Okay, so future work. So obviously we're sort of using a sort of a plausible TBV model, but it's not calibrated on real data in humans. So that's something for us to do moving forward. One thing that's quite interesting thinking about a TBV is it makes you kind of really think about what do we know about the infectious reservoir, and how does that vary as transmission intensity varies. So we need to really test like how well our model is capturing that to fully assess who are the key populations to target. So wrapping up, I'd like to thank Tom Churcher and Daniela Oliveira at Imperial College. We've had really interesting conversations with Patrick Duffy and his team at NIH, and they are carrying out these trials in Mali that I mentioned with Issachar and others in Bamako. So thanks very much.
Thank you. Any questions? Steve?
Thanks for a great presentation. I'm a bit confused about your terminology. Are you stating that if you have a cohort that has a parasite density of X that's asymptomatic and a cohort that has a same exact parasite density but they're symptomatic, that the symptomatics will transmit more than the asymptomatics who have the exact same parasite density?
Not precisely. So we don't quite have that level. So the model is quite a coarse-grained model that doesn't track parasite densities. And obviously sort of parasite densities are a complete continuum. I suppose what we're saying is sort of on average you would associate sort of symptomatic infections with higher parasite densities than asymptomatic. But I mean, I mean, one should test that quite rigorously. I mean, for example, I don't know how much skin feeding is done on, symptomatic carriers. Like, we assume that they're more infectious, but obviously if you have a very active immune system.
Yeah,
that
so
could
that's
really-
my point. I think
Yeah.
you should be more precise in your terminology
Yeah.
because if someone is ill, then they're going to have cytokines floating around, and it's quite likely that that would downregulate transmission, interfere with transmission. So if you mean parasite density, I think you should say
Sure,
parasite
sure.
density.
Yeah, no, I'll take that on board, but I would still underline that even without that, the symptomatic people are really causing quite a small contribution to the overall reservoir.
Thank you for the wonderful presentation. Actually, in relation to that, I'm wondering how much variability is there in the transmission rate in natural infections, and what kind of threshold does it set for transmission blocking vaccines?
So you mean like the percentage of mosquito bites that develop infections?
So I mean in terms of some parasites might be more transmissible than others, so you have some variation. And depending on what that variation is, the transmission blocking vaccines need a certain threshold of activity. Otherwise, you select for certain rates of transmission.
That's interesting. Yeah, we haven't considered that. And one of the things about the mosquitoes that we've taken from inside of houses is that, so we don't know who they've fed on, and whether there are drivers of some parasites being more transmissible. But that's interesting to think about.
Oh, okay, thank you.
Thank you.
Hi. Just to understand, in your study cohort, did you look at the symptomatic and asymptomatic divergence in the symptomatic and asymptomatic, study groups? And did you see the oocyst difference in different geographical areas in that particular cohort?
No. So unfortunately, because the mosquitoes were collected from the inside of houses, we weren't directly able to link them to, we didn't know who they'd fed on, which is sort of a missing piece of the puzzle. Yeah.
So do you think the TRAs would also vary with such different diverse geographical, cohorts, like different locations if you study and if you see the TRAs and
Potentially, yeah. I mean, that's really interesting because so we've got oocyst data from one sort of high transmission setting, and then the question is sort of how portable is that to other settings? The question is probably not very. So it'd be really great to see how that varies with transmission intensity. Yeah.
Very interesting. Thank you.
Thank you.
Thank you. Any question?